Hello everyone. Today, as said earlier in the previous video, we will see the crystal field splitting in the case of tetrahedral geometry. So before going to that, we will see a quick recap of what all things have to be kept in mind before going to that topic. First, we will just have an outline of crystal field theory, where there is an electrostatic model, that is, the bond is considered as ionic or an interaction of electrons only. And two types of ligands are there, anionic as well as neutral ligands. Anionic ligands are point charges and neutral ligands are point dipoles. There is charge separation in the same molecule. And coming to the metals, metals have d orbitals in them, which is taking part in the bonding. And these 5 d orbitals are degenerate. They are having same energy. And the negative charge or the negative end of the dipole from the ligands comes near this metal d orbital, their degeneracy is lost. Their energy will no longer be same. And or in other words, we can say these d orbitals are split. And the splitting is dependent on the nature of the crystal field. So we have seen in the previous class how this splitting is happening in the case of octahedral complexes, and now we'll see it in the tetrahedral complexes. Before that, we will just have a quick recap on the shape of the d orbitals. As we said, the xz, dxy, and dyz have geometry in which the orbitals are in between the axes. They are appearing in the space between the axes. And for dx square minus y square and dz square, they are appearing along the axis. They are showing the electron density in the axis of the atom. Now we will see the crystal field splitting in tetrahedral geometry. So tetrahedral geometry, tetrahedral compounds are compounds in which metal is bound to 4 ligands. And this is a shape of a tetrahedron. So this is a tetrahedron. And the tetrahedral geometry is similar to this geometry where the metal is occupying at the center of the tetrahedron. And ligands are at these 4 corners of the tetrahedron. So if we draw the axis of this metal, it will be like this: x-axis, y-axis, and z-axis. Consider this as x-axis, this as y-axis, and this as z-axis. So it is clearly evident from this picture itself that the ligands are not approaching the metal through the axis of the metal. They are approaching through the space between the 2 axes. So this is going to determine how this d orbitals are split in the case of tetrahedral complexes. So here, as we see in the case of octahedral geometry, this is a metal, a free metal ions d orbitals. Free metal ions d orbitals are at a certain energy, and when these d orbitals are in a spherical crystal field, that is when it is in a uniform crystal field, their energy gets raised. Energy gets raised because of the interaction of the ligand's electronic field. And this is given as that energy, the average energy of d orbitals in a spherical crystal field. So d orbitals of free ion, when the ligands are coming, if it is coming in a fashion such as that is uniform around the metal atom, its energy is raised. There is no splitting. But when the crystal field is tetrahedral in nature, for example, this nickel, for complexes like cobalt, Cl4 2-, they are having a tetrahedral geometry. So cobalt will be at the center of the tetrahedron, and the 4 Cl ligands are approaching it through the space between the axes. So what happens is having the shape such that they are in between the axes. That is, for example, d x y, like this. That is in between the axes. These orbitals will experience a greater electric field from the ligands. Thereby, these orbitals' energy will get raised. So these three orbitals, which are there, d x y, d y z, and d x z, energy will raise, and they will become, they are denoted as d2 levels, and these two orbitals, that are dx2 minus y2 and dz square, will be along the axis. So when they are along the axis, what happens is that the interaction of the ligand electric field is lesser for these two orbitals. So therefore, their energy will get decreased, and they are denoted as E level. Here, the G subscript is not used as in the case of tetrahedral complexes, because the overall crystal field is not symmetric like that of octahedral. And this energy difference between T2 and E levels is called as crystal field splitting energy in tetrahedral geometry, or tetrahedral crystal field splitting energy, or delta T. So here there are 3d orbitals. Therefore, the energy difference between the barycenter, that is of the energy of the d orbitals in a spherical crystal field, and the T2 levels is given by 2 by 5 delta T, and the difference in energy between the barycenter and the EG levels are given by 3 by 5 delta T. So you have to keep in mind that in tetrahedral geometry, the higher energy ones are the orbitals which are having a geometry such that the electron configuration is maximum in the space between the axes, that are dxy, dyz, and dxz. This is happening because the ligands are directly coming to that. It is appearing like, because the ligands are coming in their direction, in these d orbitals directions. But in the case of octahedral geometry, it is different, because the ligands are coming along the axis in that case here. So because of the difference in the direction in which ligands are approaching, the d orbitals are split in different ways. So like we said earlier in the previous video, this crystal field splitting energy will be dependent on the strength of the ligands that are approaching. So higher and stronger ligands will cause a higher crystal field splitting energy, and weaker ligands will cause a lower crystal field splitting energy. And this is also affecting the high spin or low spin complexes in the case of tetrahedral geometry. If you have any doubts in that case, you can visit the video on crystal field splitting in octahedral geometry. I hope everything is clear. And if you have any doubts in the topic that we have covered here, you can ask me in the comment section. Thank you for watching.